Hi, everybody. Thanks for coming. I know I'll try and keep you awake after that big, delicious lunch. I know it's a challenge. Well, so this is, those last two presentations are kind of hard to follow. I think what Dave Colasar has been saying about, and Mike Raitt about the AM station is amazing. And hearing Paul Pala talk about some of the new research they're doing is also extremely cool. My goal today, there we go, is to talk about all digital FM. And as I'm not sure if Mike said it or if Paul said it or if both of them said it, but I think that it's very likely that as all digital technology evolves and is adopted eventually, it'll probably be on a different schedule for AM and for FM. We've seen why AM might have more reason to consider that earlier than FM. One of the things that we've been focusing on a lot at NAB lately is what's happening in vehicles. And we have an auto initiative. You may have read about it in the trade press. We just came back from the radio show in Orlando. We had a couple of interesting presentations about connected cars, and later today, the last session in the program today is called Radio and the Connected Car. I'll be back up here moderating a conversation between some experts in that field. So it's clear that, and Paul did mention this point, all digital radio may be useful for the connected cities and connected cars and autonomous vehicle future that we're all facing. So very briefly, here's what I'm going to do, and some of you, this is kind of an encore presentation of something I talked about at the NAB Spring Show. I'm going to talk about an all-digital FM test project that we conducted out in Las Vegas. A week ago, maybe a little more than a week ago, I learned that my good friend Philip Schmidt is here today, and I have a special guest speaker. Philip is right here, and why don't you come and sit up here on the dais? And we've got some slides here for Philip, and I think I'm really interested in hearing what Philip has to say about some HD multiplex tests we did out in Las Vegas. So I'm going to go through this pretty quick because we only have 30 minutes, and I want a lot of time for Philip to give you his expert information on what Nautel's been doing. So we all know, I think, right now the FCC has authorized hybrid FM IBOC, FM and AM IBOC, but you may not realize that all the receivers that have been put out in the field, for the most part, are compatible with the digital signals that are specified in the NRSC standard. All digital FM has some definite advantages, but it has one, big, huge disadvantage, and that is that it's not receivable on analog radios. Just for those of you who aren't familiar with the signals, here's what analog FM looks like. This is the hybrid FM IBOC system that is authorized and in pretty wide use. And this is the all-digital signal. The analog has gone away. If you were here for Paul's speech earlier, he was talking about this area in the middle. In fact, there were some questions about that area in the middle. And it turns out that today's transmission equipment and reception equipment are equipped to populate that part of the signal. So, except of course that Nautel has some ideas about that. And Nautel's idea is HD multiplex, and I'll say very little about that because we have the worldwide expert on that subject sitting up here on the stage. So we tested, I'll just go back a slide here. On our field test, we tested this signal, which is receivable on existing receivers, and then we also did some tests on this experimental multiplex signal. So we have a lot of partners on this test. I don't know if Mike Cooney is back in the room here, but Beasley donated some airtime on their station in Las Vegas. We had Nautel, a budget group, is now a member of Pilot. Pilot is the innovation arm of NAB, and I mentioned that we have an auto initiative and we're working with auto companies, and one of the companies we've been working pretty closely with is a budget, and they contribute the vehicles for this test. Martin Stabbard from Town Square came out. He was one of our drivers and data collectors. So it was a big group. It was a really neat project, too. Our goals were pretty basic. We just wanted to exercise that all-digital called MP5 code. We wanted to measure the coverage around Las Vegas. We wanted to confirm that it works in these consumer receivers. And as a bonus, we kept the equipment after the test was done. We were out there in January and February. When we were done with the January, February tests, we left the equipment there, and come NAB showtime, we fired it up again, and we had I'll call it a quasi-all-digital signal on the air, which we were demonstrating in the North Hall Convention Center. So let's see here. This is just some information on the station we were broadcasting from. Russ Munching was instrumental in helping us get this test going. You may remember a couple of years ago we did an all-digital AM test, and to measure the coverage, we had a 25 hertz tone to the digital audio, which our test equipment detects. And that tone is only in the digital audio portion of the signal. So by looking for that tone, we can tell whether we're receiving the digital audio or not. And thanks to the magic of Russ's software, we're able to plot maps which show that. Just a couple pictures. This was the studio, was kind of our base of operations that B has in Las Vegas. This is a block diagram of the test equipment that we were using. It's pretty straightforward. These are the tone generators that I mentioned. We have these 25 hertz tone generators put into the signal path. The transmitter, Phil, correct me if I'm wrong, but wasn't that transmitter just recently installed at KKLZ before our tests?
But not for those tests specifically.
Right. Just coincidentally, and luckily for us, KKLZ had just turned on their HD radio systems just weeks before our tests.
Right.
Here's a picture of the equipment, and we prepared the tone generation equipment in this portable rack, so made it a little easier to set up. Here's a picture of the test crew. Milford Smith was working with us on this project. Some of the people that weren't in the picture are listed there in the lower left-hand corner. This picture was taken up on the top of Black Mountain, and this was the first time I'd ever taken the ride up to the top of Black Mountain, and it was a pretty exciting ride, I must say. And your Joey, he was amazing. He just tear up that mountain. I'd have to close my eyes and open them when we got there. Here's a picture of our fleet. We did the all-digital test, the real all-digital test where there was no analog on the air. We had to do those between midnight and 5 a.m. because that's when the station agreed to take their analog signal off the air. We were using two test systems in the vehicles. We were using the receiver in the OEM built-in receiver. We also had a test receiver of Russ, which provided really deep dive information into what kind of signal we were receiving. This is a picture of the test receiver, which we hooked up to one of the computers, and it would just, in addition to creating the map that I mentioned, it would also provide really detailed information on the partitions and all the detailed stuff that you might want to look at. And here's a picture of the vehicle. So we had one GPS antenna for each test computer, and then the OEM receiver in the back and the Xperi test receiver in the front. Lastly, we had these Spark HD radio, portable HD radio receivers. So we did just kind of anecdotal stationary reception tests using this receiver. And for those of you that visited us at the pilot booth at the NAB show where we were conducting our demo, you might recognize this because we had a bunch of those receivers in our booth as well. So I think I already mentioned we tested in January and February. We did the all-digital tests at night. We did other tests besides just the MP5 all-digital. We did some hybrid mode tests, and so we could compare the coverage and performance all-digital to the hybrid. Here's some pictures of the signals. These are off of the front panel of the Nautel transmitter for MP5, MP3. Now you see the analog is back. This is, there we go. This was the signal we showed during the NAB show. We had to keep the analog up during the NAB show because otherwise we would have been taking the station off of the air. During the show, we couldn't do that for a week during the day. And Philip, I think you have a couple slides about that. So let's wait, and you can go into that later when you're rushing through your presentation.
Yeah. Thank you.
So just, this isn't for reading. Just to give you some sense of the complexity of the test. We had 4 vehicles going. We completely mapped it out for each night, what mode we would be testing. We did some daytime testing. That was for the first week. This was for the second week. Was not quite as elaborate of a test. So let me talk about some of our results. Philip will go into more detail on the HD multiplex. And it did work. It wasn't reliably received on the OEM receiver. So, and that was one of the goals of the test, was just to see. It had never been done before. So once it was received, it would stay locked. And I have a map here in a second that shows you that. The MP5 digital worked great. It worked pretty much like we expected it would. And Las Vegas, of course, in the middle of the desert. And we were well into the middle of nowhere before we started losing the signal. It was just as seamless coverage as you would hope for in the city. Here's a map showing Las Vegas. These are the routes we measured, and the yellow is good. Yellow good, red bad. You can see that the Las Vegas was just completely covered. I have some close-ups here of, I don't have time to talk about it today, but we did some additional analysis on that route in particular because it was interesting to compare the performance up there between the different modes that we tested. Here's a picture of the MP5. The only dropout that we encountered is there's a tunnel under the runways at McCarran Airport. And we'd even keep it halfway through the tunnel, and then it would die, and then we'd pick it up again when we left the tunnel. So just seamless. Similarly, when the HD multiplex was acquired, it was pretty darn solid. And it was interesting, the HD multiplex test was not a real-time test. It was kind of a signal generator test where we had some vectors that we would broadcast. And they would loop every 90 seconds. And you can see these little blue points here. That's where the signal would loop. And if somebody analyzed this, they could probably tell how fast we were driving. So let's not go there. So that's what I got through pretty quick. So I'm going to turn it over to you. And now, please, you go. And I'm going to take your seat here. And why don't you go and fill us in on your multiplex stuff? It's
Sure,
really
sounds
fascinating.
good. I've got a whole 5 minutes now.
No, you're good. You got 15
No, that's
minutes.
fine. So HD multiplex is essentially a basic concept that we're proposing to, really it's more than just an all-digital solution. I'll get into that in a second. I presented this slide before, and the idea is once the FM goes away, we could fill it with more dual sideband carriers like that. And then a standard receiver could dial into any of these dial frequencies and get up to 370 kilobits. We were able to show 15 audio services. But there's 2 shortcomings with this particular slide. For one thing, you wouldn't want to do the frequency shift like I just demonstrated here because you end up with 2 even frequencies at 96.2 and 96.4. Really what you want to do is shift everything over by 100 kilohertz so that 2 of the sidebands are on standard dial frequencies and 1 would be more in the center. But HD multiplex is not just a digital solution. What it really is a digital channel combiner at the digital level. So what HD multiplex does is it can take multiply independently modulated signals from various X-gen modulators here and create a combined signal out of that. Oh, there's a couple of things missing here, but that's fine. So I guess case, we see the action modulators on the left. One of them gets shifted 100 kilohertz the other way, 100 kilohertz the other way. You add them together. But the key thing is the crest factor reduction, the peak to average power reduction. Once we add the various carriers together, our peak to average power really goes up. So what we've done is we've modified the peak to average power ratio reduction engine that we already have in our system to account for some phase shifts that we have to account for in signal A and C that's shifted. And we can then again come back to a signal that has peaks, is actually transmittable, that can easily be amplified, and can achieve reasonable power performance. So that's really what this is all about. So the way to think about this is almost more like Lego pieces. We've got all these different sidebands, and we can put them together in any which way. It doesn't necessarily have to be all digital. There's various combinations we can think about that. But here's the basic 6 sideband signal that I showed earlier stylistically, captured on a spectrum analyzer and a screenshot on the transmitter. And this we've only put off fairly quickly. We didn't do a drive test with this particular signal, but we made sure we could receive all 15 audio services. And I think it's true to say any receiver that could tune to it with the dual sidebands didn't have any issue picking it up.
And I believe we did this test with the portable receiver, which was tunable in 100 kilohertz increments, right?
Right. But I believe you also checked a couple of the other receivers that were able to get to 96.3. The Ford receiver was working fine for those as well. As long as it had the 2 sidebands, I think it was locking in just fine. Then the previous slide was in MP3 with the skinnier carriers. We then switched it into MP5 mode, and you can see it now fills up the entire frequency band there. We've also spot checked that in the same way. But because we only had experimental authorization for the main channel and the 2 first adjacents on either side, that only gave us a 96.3 tuning frequency and then 96.2 and 96.4. So that's why we came up with a couple different configurations. One that we had kind of wanted to look at is more of a 400 kilohertz mode where we muted the outside carriers and turned the insides into independent single sidebands. And the thinking here was it would be more of a central density or occupancy, more comparable to what FM hybrid is today, with about the same kind of power in the center that we would have for FM, just replace FM with HD power, and keep the IBOC power at the same power level. And that's one that we did a test drive on, mostly the belt loop. The interesting thing, once you get into single bands, you can actually get back, and you have to think through that a little bit with, it's almost like Tetris, how you put this together, but you can get back to odd dial frequencies. So this transmitter we're able to pick up at 96.1, which would have been the, I think the carrier from the left. 96.3 would have been the dual sideband, and 96.5 would have been the other one. So that would have been, the attraction here would be, the spectrum looks comparable to what we have today, and we can all tune to all these sidebands. Then another test that we've done here is we created a 500 kilohertz signal where we've taken the 600 kilohertz mode, getting a lot of echo here, and shifted everything by 100 kilohertz, but because we did not have authorization to go to second adjacent, so we dropped off that sideband and gave its power to its partner. That's why the one in the middle is 3 dB higher. So we've tested this one as well, and essentially, I think this is the next slide I have on there. That was the test road that was done on that particular carrier. And yeah, you've already talked about your repeating vectors. All the blue spots are all the various points where the vector would start over again, receiver would drop briefly, reacquire. But one of the routes also was able to pick up that signal about 64 miles out. But during that test route, they were switching back and forth to various frequencies, so it's not really a representative test route. Here, I believe that's we were driving through the strip loop. I thought that was a kind of neat representation of the signals actually going through all the cans, all the various buildings in Las Vegas, and it held up fairly well. And again, this was actually taken with the sideband as the test signal.
It wasn't just fairly well, though. I mean, it didn't drop out.
Right.
That was true.
For the repeats, yes.
Right, except for the repeats, and that was also true for the MP5 performance.
Right.
Just rock solid.
And here's a close shot of the airport tunnel that you mentioned. You can see the GPS thinks it's kind of driving into the ground for a while, and then it requires. The only place that we did notice some dropouts, they are fixed with a dual sidebands. That's where you can see the frequency diversity that Paul mentioned earlier really is kicking in. In single sideband, there was a dropout behind the shadow of Lone Mountain. You can see the transmitter site is right behind there. And with dual sidebands, those dots were solid. So overall, I mean, the algorithm itself seems to work quite well, but at this point, it's too early to do any real scientific tests on it because of the cyclic nature. We're repeating all the time, so really we need to get to a real-time modulator that can actually do this to do some more testing. So at this point, that's as far as we can take it. We only had one night to really test HD multiplex because we could only do that from 12 to midnight. So really, once we're at a better place with a real-time modulator, we should potentially repeat some of those tests and really do some more scientific analysis on those. I think we found if a receiver can tune to the dual for sidebands, they all seem to work quite well. So it's a backwards compatible mode. So this way we could potentially, already draw 50 million receivers that are out there. But the single sideband modes at this point, we should consider them experimental because not all receivers work well with it. But they potentially could have an application in data casting or a specialized receiver. The signal itself can work. It's more a receiver implementation issue. Yeah, we probably don't need to go through all of those. Right. Well, how much time do we have?
I would just say a couple words about your thoughts, Philip, on how you might use
exactly.
this.
Okay, sure, we can do that. I mean, one application area for those single sidebands, for example, if you come up with a dedicated, let's call it an IoT or data casting receiver, we could think about broadcast data for automated cars. So, for example, think about a fleet of 2,500 vehicles, a taxi fleet or municipal fleet, whatnot. Each one has a sensor. And IoT works great for small amounts of data that are point-to-point, so all the sensors feeding back information. But if you then want to send it all back out in a point-to-point form, that very quickly explodes into a lot of data. If it's data that a lot of participants in the network are interested in, it becomes a lot more cost-effective very quickly if you just do it with a broadcast. So one thing that we could do, for example, with HD multiplex, if you allocate it in such a way that the sides are today on odd dialed frequencies, well, we can dedicate those to audio services, and they're backwards compatible with existing receivers. So this configuration here, you could have 4 or 5 audio services on A, 4 or 5 audio services on C, but B, for example, could be an application for some of those new modes that Paul was talking about earlier. And with those, we could get very robust or even higher data capacity for application services. And those don't need to be backwards compatible because they're likely a custom-built receiver anyway. So I think that would actually be a really nice application for all of this. And here's another shot of the demo system, the demo signal that we had on during the NAB show with 4 independent single sidebands. And in this case, normally the intention would be that the 2 sidebands would be your normal hybrid configuration that we know and love today. And really only the outer ones would be special ones. And there's really no need to actually have both of them on both sides. You could just start with one on one side and maybe make that a data carrier. And when it comes time to turn off the FM, you can move that sideband into dual sideband mode. So that would be essentially the basic system here. All right. So I guess
we're good. We started, so you don't cut us short here, Paul.
So thank you very much for the opportunity to mention it.
See the clicker though. There you go. And I want to make
I'll
sure
stand over here. It's this microphone here is picking.
It's on. Okay. There we go. So just one point of clarification, Philip. All of those signals, all those spectrum you were showing us, those come from a single transmitter.
Yes.
Right. So that's just a single transmitter that generates all of those spectrum. So that's an important point. And I'll skip through that one, and then we thank you. And I think I have a couple of final slides here. And I guess one thing I want to point out is the test program was really serving 2 purposes. We were testing the MP5 mode, which is part of the standard, which is compatible with existing receivers, and which conceivably, if a technical record is developed, we could, we meaning the broadcast industry, could petition the FCC to allow broadcasting of that mode. Just like the FCC was petitioned to allow hybrid mode back in early 2000, we could petition for all digital mode on a voluntary basis, just like hybrid was authorized. So there's that goal, and this is really helping the industry start a technical record on this. And this was also one of the purposes of our all digital AM testing as well, was to get that technical record so we can go to the FCC. But the other piece of this was to just start experimenting with how are we going to make the best use of that spectrum. We know there's this gap in the MP5 spectrum. Philip and Nautel have been talking about HD multiplex for a couple years at trade shows, and it just seemed like this test window that we got thanks to Beasley and thanks to our other partners was just a good opportunity to just try it out, see if it worked. So, this will be a work in progress, and I'll just to the stuff we heard from Paul. Earlier today, Paul Pala was talking about Xperi's investigations. I guess, hopefully we'll see some movement on those modes in terms of a field test or actually building something and testing it too. So that's what we were trying to do here. I think it was a lot of fun. I mean, it was a good project, maybe except for the trips up Black Mountain. Just to wrap it up once and for all digital FM is something that we need to think about. It's going to be quite a while, I think, before FM broadcasters, want to turn off their analog, and we need more receivers in the marketplace at the very least. But that doesn't mean we shouldn't be looking at it. We need to be looking at it now so that when that time comes, we're ready, and that's really what we're trying to do. So again, thanks to all our partners, and thanks for having us here today.